This is lesson 4, linear growth and decay nth rule. The learning goal is to write a rule for a linear growth or decay sequence, and to also see the difference between what a rule is and what a recurrence relation is. The success criteria is to be able to apply the nth term rule for monetary examples, and to be able to write an nth term rule given any scenario that has growth or decay. Now you'll notice that the screen is just a little bit bigger than usual, and this is because before we get to the actual set notes, there is a PowerPoint presentation that I have created in order to see how this rule works and where it comes from. So before we get to that, as you can see, you can generate as many terms as you like with a recurrence relation, but to find any term, you must find all the previous terms. So what that means is if I had a very simple 8, 11, 14, 17, etc. We know that we are counting up by 3 with the starting value. If I wanted to see what the 27th term is, I need to rely on the 26th term and add 3 to it. But I don't know what the 26th term is without the 25th or the 24th, etc., etc. And this is where we can use a rule, and this rule can be used to calculate any term in the sequence directly, given that you have what the initial value is and what the common difference is. How this rule works is let v of n be the value of the nth term. So for growth, the rule to find the nth term is given by v of n is equal to the initial plus n times the common difference. And if you're looking for the 16th term, or a 16th iteration rather, you will just plug in 16 times whatever the difference is, and you add that to the initial amount. For decay, the rule is the same, but instead of plus, it is minus. And if you're trying to find a common difference where a percentage has been provided, you will use this formula here like we did in the previous lesson. To get a better feel of this, we're going to have a look at the theory behind what's going on here. Let's have a look at the following sequence. So here we have a sequence that starts with 8 and goes up by 5 each time. So the starting value, v of 0, is 8, and the common difference, d, is positive 5. Now this keeps going on by the ellipses here to indicate it keeps going on, and it's a pretty straightforward sequence. So we're going to look at what patterns we can establish. All right, so a common difference is 5. This we know. Our initial value is 8, just an arbitrary value that has been established. To get v1, we need to get v0 and add 5. Or in this case, we need to get 8 and add 5 to get 13. That makes sense. And this is where you get 8 plus 5 is equal to 13. To get v2, we need to then get v1, which is 13, and add 5. But we also know that v1, how we got v1 in the first place, was just getting v0 and adding 5. So to get v2, which is this one here, let's get v0 and add 5, and then add 5 again. So v0 plus 5 plus 5, and this will give us a v2, or our third term. But what I want you to notice is that the amount of 5s that are being added. Here we can see that there are 2 lots of 5s that are being added to the first term to get v2. Alright, so this is why we've written that instead of this, we can write it as v0 plus 2 times 5, or 2 lots of 5. Which ends up being 8, which is the starting value, plus 10, 5, and 5. And this will give us our 18. So I could have just written this as v1 plus 5, which is this plus 5. But if I want to reference the initial value, I'm going to write v0 and add 2 lots of 5. And again, I'm going to do this with v3. So this is v0, v1, v2, v3, 23. You get 23, obviously recurrence relation rule, we can just get v2 and add 5. Or we can get V0, add the two lots of 5, 1, 2, and then add another 5, and it's just cut off a little bit. That should say plus 5 over there, plus 5. So we've got this 2 5s, and we add another 5. And how many 5s is that all up? That will be 3 lots of 5s. So V0 plus 3 lots of 5s, which is 8 plus 5, 10, 15, which gives us a 23. So apologies, this is cut a bit. How about if we could just move it a little bit there and maybe a bit down? No, it doesn't let me down. Okay, that's right, and 23 here. And what I want you to notice is, can you see a link between the iteration number and how many lots of common differences there are? This is the foundation of the rule. 3, 3. So depending on what V position you are looking for will dictate how many times you're going to implement the common difference. So the general rule to find the nth term for the sequence, so if to get V1, we get V0 and 1 lot of 5. V2, we get V0 and add 2 lots of 5. For V3, 3 lots of 5. For V4, 4 lots of 5. To get V of n, we get n lots of 5, and n is just however many iterations you choose to put in. So if I want to get, for that specific sequence, V of 32, all I have to do is get the initial value and add 32 lots of 5 to whatever the initial was. That's all there is to it. But we now want to generalize this rule. In this case, we used a starting value of V0 and a common difference, which is also called D. We used 5 for the previous example, but we want to generalize this even more. So we're going to replace the 5 with the letter D. And here we can see V0 is our starting value, N is the position, and D is the common difference. And this is where the rule comes into play. If you can tell me what the initial amount is, what the common difference is, and how many iterations you can get, that you want, I can give you what that value of that sequence is. So now you got this bit of background behind where this rule comes from. We can use this rule now to help us answer the following 2 questions. The first question has a look at the following recurrence relation can be used to model a simple interest investment of $4,000 paying interest at a rate of 6.5% per year. We need to find the following: how much interest is added to the investment each year, write the recurrence relation to the model to the situation, write the rule to calculate the nth term, use this rule to find the value of investment after 15 years. I'm also going to use this rule to find the value of the investment, find when the investment first exceeds $10,000. Okay, let's have a look here. Let's break this down. Let's first look at how much interest is added to the investment per year. Now we know that this is 6.5%, and all we do is 6.5 over 100 times the initial amount of the investment, which is 4,000. Hopefully by now this should easily come to your head when working out. The amount of interest is $260, simple interest that is added. Simple, very simple, no pun intended. Question B is looking for a recurrence relation to model the situation. So a recurrence relation always starts off with V of 0, so the initial amount, and in this case it's 4,000, and V of n plus 1, so to get the next term, you get the previous term, V of n, and because it's an investment, we're adding $260 each time. Pretty simple. I'm going to start writing on the side here because I run out of space. For C, we're going to write the rule to calculate the nth term for the situation. Now, if we want to write a rule, the rule is as follows. It's V of n is equal to, and we have to choose either this one or this one. Because it's an investment, we're going to use the plus. So it's V of 0 plus n times D. Now, we know what our initial amount is, so we can replace V as 0 or 4,000. The N is still going to stay the same because we're just using this as a rule. So we'll keep it as N. And we're going to times this by the common difference, which in this case is 260. Now, this is sloppy notation. All we did was just a straightforward substitution. So let's just tidy this up a little bit. This is 4,000 plus 260 N. So when you're timesing a letter and a number, you always put the number in front with the letter tagging along and remove the multiplication sign. Now we've got a rule. We're not necessarily using the recurrence relation now. We don't have to refer to previous numbers. We can just jump straight to whatever term we want. And this is going to help us with question D. Use the rule in C to find the value of the investment after 15 years. Or in other words, we're just finding V of 15. And anywhere we see an N, we're just going to replace it with a 15. And that's all we've done here. Because we're adding 15 lots of $260 each time. So after 1 year, it's 260. After 2 years, it's another. We're doing this for 15 years. So we're doing it 15 times. This ends up being $7,900. Now this is how much is in the account. Okay, so be very careful. This right here is just purely the interest amount. But this value is how much is in the investment after the 15 years, including that 4,000 initial. Question E, use the rule to find when the value of the investment first exceeds $10,000. So in other words, when we hit $10,000, we need to find what value of N we need to plug in, this N value to plug in to get $10,000. Now there are numerous amount of ways. You can use a solve function on your calculator, or you can work this out algebraically. Hopefully by now you should be used to these skills. This ends up being, N value ends up being 23.0769 2308. Now N is just how many years. We look at this value and we think, 23.07692308. Well, let's just be safe and round this up to approximately 24 years. Because we can say that within the 23rd year, yeah, we'll hit $10,000 with an interest. But just to make sure to play it safe, we'll always round up the time frame. Okay, we don't round down. If we round down, we round down just to 23, we haven't necessarily hit that 10,000. We have to take that a little bit of 0.7 of a year to get to 10,000. So to play it safe, we round to 24. So in this case, it exceeds 10,000 after 24 years. The second and last question looks at a coffee machine that's purchased for $6,000 and its value depreciates at a flat rate of 5% per annum. First question looks at how much does a coffee machine depreciate each year? So we need to find out what 5% or 5 over 100 times the initial amount of the coffee machine and see what this price ends up being. And this is $300. So this depreciates at $300 per year. So a common difference, D, is equal to negative 300 because of the word depreciate. So just be careful of the context. B, write a recurrence relation to model this situation. We always, with recurrence, write V is 0. We have to write our initial amount. And to get the next term, V of n plus 1, this is equal to the previous term, V of n. And because it's depreciation, it is take away 300 because a common difference is 300. So that's our recurrence relation rule. C, write a rule to calculate the nth term for the situation. If we're going to write the nth term, So V of n is equal to V of 0 plus or minus, in this case it's going to be minus n times the common difference d. Now we know what our initial is and we know what the difference is, so we can just replace that accordingly. The V of n is equal to 6,000, take away common difference 300, and just have that little n tag along. So we know after a certain amount of years, so maybe after 6 years, we just get 6 lots of 300 and subtract that from 6,000, and that will tell us what the price of the coffee machine is after the 6th year. So question D, what is the future value of the coffee machine after 12 years? So we're just finding the V of 12. In any way we see the letter N, we're just going to replace it with 12. Put this into the calculator and you'll end up with $2,400. So the price of the coffee machine is $2,400 after 12 years. And this concludes this lesson. Go ahead, check your log sheet, see which questions you need to do, and I'll see you in the next video. Bye bye.